So, welcome back. We're going to continue on finding limits algebraically. Okay, and what we have here is we're going to go through two examples of how to find limits using what's called the conjugate technique. The first thing is when you're given a limit, like so, the first thing that you always want to do is try to see if this function is continuous. And if it's continuous at C, or the x approaches C, then you're going to have what's called direct substitution will work. So by doing so, what we're going to do is we're going to plug in, and direct substitution literally is where we take x as approaches C for the function, and that should equal f of C. All right? This only works if the function is continuous at C. Okay? It's only continuous at C. So we're going to first test that out. So I'm going to take our C value. Our C value in this case is 9. We're going to plug it in here. So 9 minus 9, of the square root of 9 minus 3. And we have 0 over 0. Now 0 over 0 is indeterminate form. Okay, indeterminate form. And indeterminate form refers to that there is usually a hole, all right, at x equaling C. So at this point 9, we have a hole in our graph. This is known as removable discontinuity. Now, because there's removable discontinuity, we obviously know that this function is not continuous here. And we have our value of 0, 0. Now, some students think that, okay, if I have 0 over 0, that means there's no limit, the limit doesn't exist. Well, in actuality, the limit usually does exist. 0 over 0 tends, 95% of the time, or maybe more, that the limit does exist because there's simply a hole. As you approach from the right and left side, you're actually going to approach a value. So how do you solve this? Well, since I see that there's a square root here, all right, square root here. Square roots generally mean that we want to try what is called the conjugate. All right, we're going to use the conjugate technique. Now, the conjugate technique is we're going to eliminate this hole by taking our function, x minus 9, over the square root of x minus 3, and we're going to multiply it, the numerator and denominator, we'll multiply by 1, and we're going to multiply it by the square root of x plus 3. We're going to multiply by the conjugate of the square root expression. Oops, I had a 3 there, sorry. All right, and what we have is x, then we have plus 3, and we have this. Now, when we do this, generally great things happen to those that go through this, because as we go through, we have our numerator. Now, don't multiply through, square root of x plus 3. But the denominator, we take x times x, or square root of x times x, which is x. We take our middle terms, because they're conjugates, will cancel out, and then with negative 9. We can now see that this factor and this factor cancel out. And now we're left with the square root of x plus 3. Now from here, we can take the limit, because now we eliminated the hole at x equaling 9. And so now we can finish our limit by looking at the top, and now taking this new expression where the hole's been eliminated, and now take the limit as x approaches 9 in this case. From here, we plug in 9, direct substitution again, because we have now created a function that is continuous, all right, because we eliminated the hole, and we find out our limit is actually equal to 6. So this function has a limit as x approaches 9 for the square root of our x minus 9 over square root of x minus 3. We can say that this limit actually equals 6. Okay, let's try another one. And there we go. We have the limit as x approaches negative 3 at the square root of x plus 7 minus 2 over x plus 3. Now to solve this one, we're going to do the same thing, direct substitution. Plug in 9, and we have, plug in negative 3, sorry. Negative 3 plus 7 minus 2, or x plus 3. And what we have is 0 over 0 again. Okay? Once we get 0 over 0, we know we're going to have to do some additional work. Okay? 0 over 0 means the direct substitution doesn't work, and we're going to have to use, well, I see the square root, so that means we'll probably use the conjugate technique. Or I will use the conjugate technique. So we're going to use this. It's 3. The conjugate we're using is the one that's associated with the square root. So we're going to have the square root of x plus 7 plus 2. And we have to multiply this by 1 because we can't just multiply it by just that by itself because that would be illegal. All right, and improper to do. Okay, so once we have that, our goal now is to eliminate, all right, probably this x plus 3 because that's what gives us our 0. By doing so, we have this times this, which is going to give us x plus 7. Middle terms will cancel out. Left with minus 4. At the bottom, we have x plus 3. And then we have the square root of x plus 7 plus 2. All right, when we simplify this, we have x plus 3 over x plus 3. We have the square root of x plus 7 plus 2. These cancel out. We're left then with 1 over the square root of x plus 7. And now we just eliminated the whole. And so now we can take the limit as x approaches -3 here. And what we have is 1 over 4, 1/4. And that is our limit. So it's not too bad. This is a very common integral what you're doing. The strategy we're using once again is a conjugate. All right, the conjugate. And why are we doing that? Because we get 0 over 0, all right, and we see a square root, and we're going to take the conjugate of that square root to simplify and eliminate that whole, all right, that undefined value at -3. Well, I said we're going to use 2, but I want to do one more, all right, one more just for an extra bonus problem of the conjugate technique. All right, so here's another strategy. All right, once again, we plug this in here, and we have 0 over 0. 0 over 0. Notice I have the square roots. Actually, I have 2 of them. So I'm guessing in order to simplify this, we're going to use a conjugate. Okay? Why? Because we see the square roots. Okay? Square roots are the kind of the key indicator, all right, in the function, and when we get 0 over 0, that's the main thing. Not all square roots, well, you have to use that, but a lot of times you do. So when we have this, we're going to eliminate this hole because it's indeterminate form. There's a hole here, all right, hole at x equaling 0. So to do this, we're going to take the square root of 5 plus y minus the square root of 5, and we're going to multiply it by its conjugate. So the square root of 5 plus y minus the square root of 5 all over the square root of 5 plus y minus the square root of 5. Don't forget your y at the bottom. And let's simplify. So here, all right, first these, using a little FOIL action, we have 5 plus y, the square roots cancel out. Middle terms will cancel, and then with this negative square root of 5 times this negative square root of 5, which turns to be, see, I didn't want to do that, so I have to use a conjugate. Some of you probably already noticed that. All right, good, because what we have right here is we're going to have negative square root of 5 times positive square root of 5, which is going to give us negative 5 itself. We have y, all right, and we have the square root of 5 plus y plus the square root of 5. These will cancel out. All right, we have y over y times the square root of 5 plus y plus the square root of 5. These will now cancel out. I like making sound effects. I cancel out things. That's a little weird, but okay, it's just the way I am. All right, now we have eliminated the whole at 0. So once we have that, we can now take our limit as y approaches 0 in this case. And as we approach 0, we get 1 over the square root of 5 plus the square root of 5. That's going to be 1 over 2 square roots of 5. Multiply the square root of 5 over the square root of 5, just to make this a little bit more proper. The square root of 5 over 10. All right. So, went through 3 examples of how to find the limit, all right, when you get 0 over 0 and you have these square roots. This is what's known as the conjugate technique. So I hope this helps you out with all of your other math problems, and hopefully you don't find finding limits that hard anymore, especially algebraically. All right, good luck and God bless with the rest of your problems.